Welcome to the European Space Agency ESA. This is the Robotic Learning Centre, and I'm here to help you find out more about Newton's 3 laws of motion. Maybe you've heard of Newton before. He is the scientist who got hit on the head with an apple. At that time he was studying motion, trying to understand the concepts behind it and how they relate to things we experience in everyday life. When Newton recovered, he realised something important. He already knew that an object accelerates only when a force acts on it. Therefore, if the apple were moving, it could only accelerate if there was a force acting on it. He called this force gravity, and to this day we measure all forces, including gravity, in newtons. Newton came up with 3 laws of motion, laws that describe how forces and objects relate to each other. So we're going to hear from Pedro Duque and Alexander Kaleri. On board the ISS, gravity has very little effect, so everything there is almost weightless. Hi Pedro. That's a nice smile you've got there, Pedro. Not much is happening. The ball is just hanging there in mid-air. Pedro blows on it and it moves because of the force of his breath. Now the ball is moving again, except this time Alexander has stopped it with his hand. And this time, nice move. Pedro changes the ball's direction by applying a force. What you've been seeing are illustrations of Newton's first law of motion. This states that every object in motion or at rest remains in that state unless an unbalanced force is applied to it. The state of motion is the speed and also the direction. The two combined, speed and direction, are what we call velocity. An object at rest has a velocity of 0, and it stays at rest unless acted on by a force. We call this tendency inertia. Here you can see Pedro applying a force to the ball. He is changing the ball's direction, therefore changing its velocity. In the second experiment, you see Alexander stopping the ball. Here he's changing the speed, therefore he's changing its velocity. The rate of change of velocity is called acceleration. Let's see what our schools have to show us. Pushing the skateboard. That's a force, isn't it? The skateboard moves, hits the pillar and changes direction. But the apple keeps going. That's because this time the force is only applied to the skateboard and not the apple. That's why eating in space isn't easy. The spoon stops, but the food keeps going. Ooh, that looks nasty, and that's why we use seatbelts. If we were in a weightless environment like the ISS, then he would continue to move, but on Earth, gravity pulls him back down. But when the support is removed, the force of gravity, now unbalanced, pulls them to the ground. Without the force of gravity, they would just stay afloat, just like on board the ISS. So, that's Newton's first law. An object at rest stays at rest unless acted on by a force. And an object in motion will stay in motion unless acted on by a force. That's a novel way of choosing whose turn it is. But whose turn for what? That's impressive. That's really impressive. Working out is obviously easy in a weightless environment. Let's see you try that on Earth. Not so easy, but I guess that's the difference between mass and weight. You might think this has something to do with weight. Well, you're nearly right. Not just weight though, but mass. Mass is the amount of matter in an object. Weight, however, the feeling of something being light or heavy, is caused by gravity acting on the object. Pedro and Alexander are floating in the ISS. Because gravity has no effect, they feel weightless, even though their mass is the same as it is on Earth. You can see Pedro lifting another astronaut, Umberto Guidoni, here on Earth. Umberto's mass is not that much different to Alexander's, but because he's on Earth, what Pedro's feeling is his weight. So, how does mass come into the second law? This science stuff is very serious. One ball is wooden and the other is brass. This time we have 3 balls. We're adding a ping pong ball. You can see here that things with more mass move more slowly. The second law says there's a connection between force, mass, and acceleration. So, if you apply the same force to objects of different mass, they will accelerate differently. So, Newton's second law states that force is proportional to mass and acceleration. So the greater the mass, the slower an object will accelerate when the same force is applied. Pedro blows the balls with the same breath, but their different masses mean they move at different speeds. Newton's second law is easier to demonstrate on the ISS, but here on Earth there are other factors to complicate things. You might be thinking that the single one will land first. In the other experiments, the lighter object travelled faster, but they land at exactly the same time. We've got a crumpled page and a regular page. They've got the same mass and they're dropped from the same height, so they should land at the same time, right? But no. One of these factors is friction. Friction is the resistance between surfaces as objects move against each other. It causes objects to slow down or stop. If there was no friction, they would keep going. This complicates proofs of Newton's laws, especially because different surfaces create different types of friction. This is why we skate faster on the ice or in a smooth corridor. So, what about the papers? Was there friction acting there? Well, there was friction between the objects and the air. It was due to friction that the flat page landed after the crumpled page. The flat paper has a greater surface area and is slowed down because it experiences more air resistance. If this experiment were conducted in a vacuum, the 2 pages would land at the same time. But why did the sack of apples land at the same time as the single apple? Well, that's down to a unique feature of gravity. The sack of apples with a greater mass and the single apple with less mass are both attracted by Earth's gravity. But gravity pulls more on the sack of apples than on the single apple. But if something has a greater mass, it needs a greater force to accelerate, right? So that, in the end, both have the same acceleration and hit the ground at the same time. Newton came up with 3 laws of motion, laws that describe how forces and objects relate to each other. Hi Pedro, Alexander. We can see that they're floating. They're pushing against each other and move apart. That's an ISS battery and it looks heavy. That means it has a lot of mass, right? Once again, they're pushing against each other, but Alexander moves less. What we see this time is that for every action, there is an equal and opposite reaction, Newton's third law of motion. Alexander pushes against Pedro, action. This causes Pedro to move, reaction. At the same time, Pedro pushes against Alexander, action, causing Alexander to move in the opposite direction, reaction. And they moved an equal distance. Action equal opposite reaction. The battery's mass is about 80 kilograms, so now the force is the same, but the mass is different. Remember Newton's second law of motion. Action and reaction are caused by the same forces, but they're expressed through different mass. Therefore, Alexander moves less. Let's see what the schools are up to. Here we go. This is like Pedro and Alexander on board the station. We add another girl and they don't travel as far. The force of throwing the ball makes her move backwards. The third law helps us in other areas too. Space vehicles use it to lift off. The air or gas is heated up and forced from the exhaust, action, and the reaction pushes the rocket up into space. Now you know about Newton's 3 laws of motion. Law 1 states that objects at rest or in motion stay that way unless a force acts on them. Law 2 says that the force is related to mass and acceleration. And Law 3 says that every action has an equal and opposite reaction.